Good morning. So today's lesson is actually the last part of this part, Combinatorics, and then let me give this a title. But before that, I will give you some warm-up problems, and then we continue. So today's lecture would be about Binomial Theorem. Okay, but before starting this new topic, let me just actually give you some examples from what is related to the previous lecture. So example. Let's solve the following equation. So we have p n and 4 plus n choose 4 is equal to 25 times n choose 5. So here we want to solve this equation for n. Of course, n should be a natural number. And because n appears here and there, n should be at least 5. Yes, n cannot be smaller than 5. So that's also something we have to be careful about. So in case that we get a natural number for the answer which is not greater than or equal to 5, we call it a false root because this cannot happen. Yes? Okay, so that's also a very simple problem. So sometimes this is not related to counting at all. So you just need to know the formulas and try to work them out. So if you want to solve this equation, you use the formulas. Hopefully you remember them or you can look them up. So this Pn and 4 is n factorial in the numerator, and the difference between these two, n minus 4 factorial. Yes. This one has an extra 4 factorial in its denominator. So this becomes n factorial divided by 4 factorial, n minus 4 factorial. On the right hand side, I will have 225 and multiplied by n factorial, 5 factorial, n minus 5 factorial. Usually, if you have fractions, if you can find a common denominator for all the fractions, it would be good if I multiply everything by that common denominator, so that I can get rid of the fractions. I hope that you agree with me that 5 factorial times n minus 4 factorial is a good choice, yes? Why is that? Because 5 factorial can be written as 5 times 4 factorial. So it means that 5 factorial is divisible by 5 factorial and 4 factorial. And n minus 4 factorial can be visualized as n minus 4 multiplied by the previous number. The previous number means 1 less than this number, which is n minus 5 factorial. So that's a good thing, yes? Because you immediately see that this combination is divisible by this, is divisible by that, and it's also divisible by that. So I multiply everything in this equation by this least common denominator to get rid of all the fractions. And everything is actually ready. So if I multiply this here, this n minus 4 factorial, and this is gone, what is left for me is 5 factorial, which is supposed to be multiplied by the numerator. This becomes 5 factorial multiplied by n factorial. Yes? And now if I multiply this by the second one, this 4 factorial in the denominator will cancel this one. N minus 4 factorial will cancel this one in total. So what is left for me is just a 5, yes? And I multiply 5 there, so it becomes 5n factorial. And now I multiply this by the last one. So 5 factorial and 5 factorial are simplified. N minus 4, 5 factorial, n minus 5 factorial are gone. So what is left for me is just n minus 4 that I have to multiply in the numerator. So it becomes equal to 25 n minus 4 and then times n factorial. Yes? Yes, is that understandable? Yes or no? Okay. And then, of course, you see that we have a factor of n factorial appearing everywhere, so I can just get rid of it. I could get rid of it first, yes, it doesn't matter. But here I divide everything by n factorial, so this becomes 5 factorial plus 5 is equal 25 times n minus 4. And then 5 factorial is 1 up to 5 multiplied. It becomes 120, and then it becomes 125 is equal to 25 n minus 4. And I divide everything by 25. It becomes 5 equals to n minus 4. And if I move 4 to the other side, n becomes 9. And 9 is acceptable. It's not only a natural number, but also larger than 5. So n equals to 9 is the only answer to this equation. Yeah, is that understandable? So these kind of questions you also might face in this topic, combinatorics. Okay, so we can also have an example like this. For appropriate natural numbers, n and k, show that we want to prove this. N choose k minus 1 is equal to n minus k plus 2 divided by k minus 1 multiplied by n choose k minus 2. So by appropriate, I mean that, of course, I have to respect some rules. N and k should be natural, and then n should be greater than or equal to k minus 1. If n is greater than or equal to k minus 1, it is automatically also greater than k minus 2. So those restrictions we have to respect. Under those restrictions, we want to prove that this is valid. So that's also a different type of question. So here you have to prove. You don't need to count anything, but you need to prove this equality is true. So this is an identity, and you want to prove it. So it's a good point to start from the side which is more involved. In this case, I will start from the right-hand side and try to reach to the left-hand side. So for this one, I cannot do anything. So I just copy and paste that part. And then what I do, I write the formula for this. Yes. So this number factorial goes into the numerator. This number factorial goes into the denominator. And then this number minus that number, yes, and minus k minus 2 factorial will go to the denominator as well. But if you multiply the negative sign, so it becomes n minus k plus 2 factorial. Yes. And I want to simplify that. So how can I simplify it? So you see that I have a factor of n minus k plus 2 here, but I have n minus k plus 2 under the factorial sign. But you can use the normal trick as you usually do. So you just copy and paste the first part. But for the second one, you write n factorial and then k minus 2 factorial. So what I'm supposed to write for this is clear. I write n minus k plus 2, but multiplied by the previous number factorial. So I have to subtract 1 unit from it to get the previous number. So this becomes 1 factorial. The motivation behind that, because I see that this factor and that factor will cancel out. And then what is left for me in the numerator is n factorial. And in the denominator, you see I have k minus 1 will be multiplied by k minus 2 factorial. What can I write for that combination? K minus 1 times k minus 2 factorial. K minus 1 factorial. Thank you. So this becomes k minus 1 factorial, and then I will have n minus k plus 1 factorial. And if you want, you can write it in this form. N factorial, k minus 1 factorial, and let me just rewrite it again in this form. Yes. And now hopefully if you remember the formula for n choose r, this is n factorial, r factorial, n minus r factorial, yes? If you compare this original formula with this, you see that wherever I have r, it has been replaced by k minus 1. So that is nothing except n choose k minus 1. And then you see that's exactly the left-hand side. Yes, understandable? Okay. Okay, now we go back. We actually start this new lesson, Binomial Theorem, which is actually a very important theorem in mathematics. So it's simple, very simple, but discovering the general formula. Newton actually did this for the first time. Let us see what is the content. The content is this. So let n be a natural number then for all real numbers so here I emphasize that n is natural, but these numbers that I want to mention are all real numbers. For all real numbers, let me call it x and y, we have this formula. So we have x plus y to the power of n is equal to sigma n choose k x to power n minus k multiplied by y to the power of k. K goes from 0 to n. So this formula is called Newton's binomial theorem. Okay, I want to try to make it simple for you. That's not actually a hard theorem. So let me start with the motivation first. By the way, if you don't mind, let me also write it in expanded form. In expanded form, it means that I have to choose k0, 1, 2, up to n, and add these terms up. Yes? So if I put k equal to 0, what will happen? This becomes n choose 0. This becomes x to power n minus k, but I have chosen k0, so this becomes n. And then y to power 0, which is y. The second term After k is equal to 0, it becomes k equals to 1. So then it becomes n choose 1, x to power n minus 1, y to power 1. The next term would be n choose 2, x to power n minus 2, but y to power 2. And then I continue this sum until I reach the last one, which is k equals to n. But before that, let me also write it for, so if I choose k equals to n, what will happen? Then I will have n choose n. This becomes x to power n minus n, which is x to power 0, which is 1, but this becomes y to power n. But this is clear that the previous step, I choose k n equals to n minus 1, and then I will have x to y to the power of n minus 1. So yeah, these are exactly the same things, but this is in the expanded form. Okay, but momentarily forget about if this formula looks a little bit complicated. Don't worry about that. This becomes clear in a moment. So forget about this. Let me just talk a little bit about the motivation behind that. So if I ask you x plus y to power 1, what is it? You really don't need to do anything. Everyone knows that the answer becomes x plus y. And if I ask you what is the answer to this to power 2, in Math 2C, you studied the algebraic identities. That's a very, very famous pattern. So you can write it as x squared plus 2xy plus y squared. But the point is that the natural question is that how can I write a formula for the general case if I increase these powers from 2 to 3, 4, 5, etc., etc. So that is the answer. That is the answer for any natural number that you like, yes? For example, if I write x to power 3, of course, this is also sometimes, all the time actually, in the formula sheet, but might be you don't have it in mind. But if you do it, it becomes x to power 3 plus 3x squared y plus 3xy squared plus y to the power of 3. Yes? So the question is that if I continue this list, what will happen if I reach to n? And this is the answer. Yes, so this is the content of this theory. So for example, if you think that these coefficients are a little bit strange, they are not that strange. As you will see why this comes naturally into the problem. Here, what is the first one? If I want to insist to write something, this should be n choose 0. But n here is 1, so this becomes 1, 0. And the next one would be 1, 1. But if you are patient enough and calculate these two, both of these are exactly 1 and 1. But when it comes here, what you have here is actually 0, 2, because n is 2 here. This number is actually 2, choose 1. This number is actually 2, choose 2. Okay, for example, in this case, this number is 3, choose 0. This will, if you calculate 3, choose 1, you will get 3. If you calculate 3, choose 2, you will get 3. If you calculate 3, choose 3, you will get 1. Yes, that is the idea. But how this is related to combinatorics, you see, this is very interesting. So might be it was not easy to predict that this is the connection between algebra and combinatorics. Of course, you can prove this formula using mathematical induction, but it might be harder, much harder probably. But combinatorial argument, why this is equal to this, is not that hard. Okay, so let us understand the problem. Let us consider the simple case of this. Okay. So this can be written as x plus y multiplied by x plus y multiplied by x plus y. So when you multiply these two binomials, what do you do? For example, you take So in each one of them, you have two options. Either choose x or choose y. For example, if I choose x here, x there, and x there, and multiply them, what do I get? I get x cubed, yes? Is that understandable? But I can choose x from here, and y from there. So what do I get? I get a term, x. So in the first case, it was x times x times x, which gave me x to the power of 3. In the second one, I can get x. I take x again from the second one, but I take y from the last one. It will generate x squared y for me. Yes? But the point is that in how many ways I can generate x to the power of 3. Don't think about formulas, just intuitively. If I want to generate x to power 3, how many ways I can generate x to power 3? If I want to have x to power 3, it means that I am forced to take x from here, there, and there, yes? Is that clear? So there's only one way for me to generate x to power 3. But do you think this is the only way to generate x squared y? I want to generate x squared y. So it means that I need two x's and one y. One possible way was the way that I did it here. I chose x from the first, x from the second, and y from the third. What can you tell me another combination that gives rise to the same algebraic expression x squared y? It's very clear. How many of them are there? I can take x from the first, y from the second, but x from the third. Do you agree that this will give rise to the same algebraic expression? Yes? Is there any other way to make x squared y? Yes. What I can do, I can choose y from the first, x and x. Is that right? And this will give me x squared y. Now tell me, is there any other way to generate x squared y in this case? No. Yes? And that is exactly why you see 3 here. Because there are only 3 cases that can generate x squared y. Because you know that when I start multiplying things, when I multiply things, at the end, I have to add similar terms. But x squared y appears in 3 different cases. So it means that if I want to add, at the end, after expansion, I have to add them up. So what will happen? It becomes 3x squared y. And this is important so that you have this coefficient 3 here. Let us check the other scenario. It might happen that I choose 2 y's and 1 x. So it means it might happen that I have this case. It will generate for me xy squared. But again, xy squared can be generated in 3 different ways, yes, in this case. So what is that? I can write y times x times y. I can write y times x. This is xy squared. It's also xy squared. Is there any other way that I can generate xy squared in this case? The answer is no. So this is the reason that the second one is also 3. Yes? So this means that this will give me 3. And finally, I want to generate y cubed. So y cubed can be generated only in one way, and then I have to choose y from here, there, and there. Otherwise, I will not have enough y's. So this means that I have one choice. Yes? It's y to the power of 3. Is it clear? Okay, but before understanding it better, let us do it for number 4. So it is not hard to see that the coefficients should be 1, 3, 3, and 1. And that's exactly what you have in formula sheet. But usually you don't have x plus y to the power of 4 in the formula sheet. So let us see if we can understand it from this perspective. And then hopefully it becomes clear for you that why this formula should work. Okay, so So let us consider this case, x plus y to the power of 4. So one way is you really don't need, so this means that I could have given you this in Math 2C, and in that case, so one way to do it is to write it 4 times and take your time to expand that. That is completely possible. But now we want to see this in a smarter way, yes? Okay, so what are the possibilities? Can I generate, by the way, can I generate x to the power of 5 here? No, because I have at most 4. I have exactly 4 pairs of brackets. Even if I choose x from all of them, I can at most generate x to the power of 4, yes? So here, and then one more thing. So here, if you see there is something going on here, you see here, I have always 3 terms involved. So here the power is 3. Here the power is not 3, but the power is 2 and 1. If you add them up, it becomes 3. The powers are 1 and 2. If you add them up, it becomes 3. And the power itself here is 3. So all the powers, all the sum of the powers in each term is 3. Yes? And what is here, probably you expect what's going to happen. Okay, in how many ways I can generate x to the power of 4? So let me just do it a little bit differently. What are the possible combinations that I can have when I expand? One possibility is x to the power of 4. Another possibility is x to the power of 3.
And then y.
And then y. One other possibility is what? I have x to the power of 2, y to the power of 2. Yes? And another possibility is x, y to the power of 3, and finally, y to the power of 4. So hopefully you agree with me, these are the only possible combinations that might be there in the expansion. But now the point is that if you want to, you can write it in this way. So from the beginning, you already know what will be the form of the expansion. Yes? So what is the form of the expansion? If I ask you what is x plus y to the power of 4, you will realize that I will have x4. I will have x to the power of 3y. I will have x to the power of 2y squared. And I will have x to the power of xy to the power of 3. And I will have xy to the power of 4. So this is not hard. The hard part is finding the coefficients. And the coefficients, by looking at it in this way, is also simple. In how many ways I can generate x4? x4 can be generated exactly in one way. And that is, I have to choose x from all these pairs of brackets. So this means that x, and x is the only combination that will give rise to x to the 4. So what you expect for the coefficient is what? Is 1. Yes? But let us look here. I want you to predict what will be the coefficient of x to the power of 3y. So this means that I have to see that in how many ways I can choose x and y from each bracket so that it gives rise to this combination. So this means that I have to choose 3 x's and 1 y. So what are the possibilities if you want to write it down? So one possibility is to choose x, and y. Yes? Another possibility is x, y, and x. Another possibility is x, y, x. And finally, y, x. Can you see any other combination which gives rise to this? The answer is no. So how many of them are there? 4. Yeah. So it means that you have 4 here. Yes. So this package is finished. Now let us consider x squared, y squared. We have to be a little bit more careful. So x squared, y squared is x, y, y. This is one combination. So another combination, can you help me? Because I don't want to lose anything. So what is that one? So x, y, x, y. Okay, and then?
2y and then 2x.
So is there any way that I can start with the x? Yes. So let me write x, y, and x.
And then at the beginning.
Can I start with an x still? Yes or no?
No.
No.
Apparently no. Okay, and then let me start with a y. So this means that I can change x's to y's and y's to x's, yes? So this becomes y, y, x, x. This becomes y, x, y, x. And this becomes y, x, x, y. So I hope that you agree with me there are no other combinations that I make it here, yes? So how many of them are there? 6. So it means that this number, whatever it is 6. Yes? Okay. And then, do I need to count x, y, 3 again? Because that is the same thing, but x and y are interchanged, yes? I can call x, y, I can call y, x. So definitely, if you don't believe, you can just check it again, but definitely I will get 4 more. Yes? And then I will have 4 here, and then I will have 1. Yes? So this is one way. I hope that you understand this is possible. Okay? So this means that I am now, instead of doing it case by case, let us now that we have learned a lot of counting techniques. So the point is that I want to count the number of these combinations. Do you have a counting strategy? Because if I can count without writing them down, then it means that that number is the coefficient, and then I will be done. Okay, if I don't want to write them down, but still I want to count them, you have a counting strategy. So let us just look at this case. Here I have written every item down, and after it is finished, I started counting them, and I got 4. But now change your strategy. Could you predict the number is 4 before writing them down? So what is that one then? It's a choice problem. You are choosing something, yes? Because, so can you tell me how it works by this counting tricks? Yes, Ruben?
4 factorial divided by 3 factorial.
How?
Because there's 4 different places and there's 3 x's per side.
Okay, so you are using the permutation with repetition. That's very good, actually. I was thinking a different way, but that's also working. Thank you. So Ruben is saying that I have 4 items. Sorry, 4 positions. But I want to look at all permutations of 3 x's and 1 y's. If they are all different, then that would be 4 factorial. Yes? But now they are not all different, so this becomes 4 factorial divided by this number, the repetition of x's, which is 3 factorial. That's the answer. For this case, still I have 4 factorial, but 2 of them are x's and 2 of them are y's. So it becomes a 2 factorial here. Is that understandable? Okay, and then for example here, I will have 4 factorial again. I have to have 3 y's, so it becomes 3 factorial. If you don't mind, let me also write 1 factorial here, because I have 1, because I want to find the pattern, yes? And here I can also write 1 factorial. But there is a better way to write this number. What is that number? This is 4 choose 1. Yes? So here, if you want to, you can write it 4 factorial and then divide it by 0 factorial and 4 factorial. Yes? Because y is not repeated at all. So 0 for factorial. X is repeated 4 times. But this is 4, 0. Yes? And this is, hopefully, you immediately recognize that this is 4, 2. Yes? And this is 4, 3. And that is 4, 4. The coefficient is 1 here. The coefficient will be 4 here. Yes. Yeah, is that clear? So in principle, you can also look at it in this way. You can say that, okay, I want to have 3 x's. I choose 3 of these pairs of brackets by crossing them. For example, I cross here, here, and here. So it means that I choose these and choose x from them. So in how many ways I can choose 3 x's out here? The answer would be a combination 4 choose 3. Yes. Okay. So I hope that it is understandable. For the general case, you really don't need to do anything extra. So that is just the extension of this argument. Yeah, is that clear or not? Yes. Okay, so this is what I want you to learn. This formula will be given to you in the formula sheet, but we try to learn how to use it by some examples. So some examples might be a little bit hard. But one thing that I want to mention here, be careful. There is a matter of confusion sometimes. Which term is this in this expansion? This is term number 1. But remember, k is 0. This is term number 2, but k is not 2. K is 1. So k is not the number, is not the term number. It is the term number plus minus 1. So here k is 0, the term number is 1. Here k is 1, the term number is 2. Here k is 2, the term number is 3. So remember, when I ask you to find the kth term, you need to be careful about which number you have to replace for k. Okay, let me give you some examples. So let me keep the formula here. For example, if I ask you to expand this, let me write it 2x minus y to the power of 5. So I want you to use binomial theorem to expand this. So what I'm supposed to do here, 2x here, 2x is playing the role of this x in the formula. And minus y is playing the role of this y. And 5 is playing the role of this n. So what you need to do, I recommend you to do it like this, yes? So what you have to do, so you start with this 1 to power 5. Okay? And then for the next term, subtract 1 unit from this power and add 1 unit to the power of the next term. Okay, so the next one you write plus. A little bit further, you write 2x to the power of 4. But times minus 1 to the power of 1. Symbolically, I write 1, but you really don't need to write it. That is my recommendation, to keep this for free space here. And then go to the next one. To the next one, it's very simple. You subtract 1 unit from this. It becomes 3, and add 1 unit to the next one, to the power of the next one. And then do the same process, yes? And then go to the next one. And, oops, I need to put some space here. And then go to the next one. To the next one, this becomes 0. The power here of x, this power becomes 0, so don't write it down. And then you write minus y to the power of 5. Okay? And now you need to fill up these gaps with these coefficients. So you know that in this problem, n is 5. So the first coefficient, if you want, by the way, what is always this answer? If you calculate and choose 0, it's always 1. And choose n is always 1. So the coefficients are always 1. If you want, you can write it down, but you don't need. So this is 1, and that's also 1. Yeah, so don't write it down. But here, what you have to write, you have to write 5, choose 1. Here you write 5, choose 2. Here you write 5, choose 3. And here you write 5, choose 4. And of course 5, choose 5 that I don't write. But in this problem, you have to carry on the calculation. Yes? That's why it becomes a little bit messy. Okay, so but you can use your calculator, of course. So what you do is this. This 1 to power 5 is 32x to the power of 5. And choose 5, choose 1. If you calculate is 5. It's easy to calculate, but you have to also consider the coefficients coming from these terms. So this is 2 to power 4, which is 16. And then minus 1 to power 1, which is minus 1. And then you have x to the power of 4, y. For the next one, if you calculate 5 choose 10, 5 choose 2, it becomes 10. And then 2 to the power of 3, which is 8. Minus 1 to power 2, which is positive 1. And then you will have x to the power of 3y squared. And if you calculate this one, it is again 10. And then the answer becomes what? 2 to the power of 2 minus 1 to the power of 3, which is minus 1. And then you have x squared y to the power of 3. And then finally here, if you choose this, calculate this number, it becomes 5. And then this 1 to power 1, this 1 to power 4. And then you have x, y to the power of 4. And finally, the only number that you have to take care is minus 1, y to the power of 5. And final step is to multiply these numbers. So this answer is 32 x to the power of 5. This becomes minus 80 x to the power of 4y. This becomes positive 80 x to the power of 3y squared. And then this becomes minus 40 x squared y cubed. And then this becomes 10 xy to the 4 and minus y 5. So the final answer is this one. Yes, is that clear? So you see, you lose the symmetry. If you don't have any coefficients here, the coefficients are symmetric with respect to the middle one. You see, 1, the last one is also 1. 4, 1 to the last is also 4. But if you have some coefficients involved, if you write it here, you don't lose the symmetry because this one is equal to this one. Do you remember I told you last time that that's an important rule that you need to remember? N choose R is always equal N choose N minus R. So for example, 5, 2 is always equal to 5, 3. Whenever these numbers add to this top number, then these numbers are the same. But when you consider the internal coefficients, then you lose symmetry. You see, there are no symmetry left. You have to be careful about it. Is there questions here? Yeah, so I will not give you some questions like this that much, but of course in the exam you will probably get one. But now let us go and look some other type of problems here. So what are you asked here? So let me write this formula here. X plus y to the power of n is equal to sigma k, and any number, it can be I, k, j, or whatever. It goes from 0, but to this number n, and then you have that number n here, the counter of your sigma here, and then you write x to the power of n minus k multiplied by y to the power of k. That's the binomial theorem. Okay, let me ask you this question. Example. So these type of examples are important to know. So example, what is the coefficient of x to the power of 5, y to the power of 13 in the expansion of 2x minus 3x minus 2y to the power of 18. So these type of questions you need to know very well. Yes, let us check this question. So here we have a binomial, an expression with two terms to the power of 18. And we are not interested in the expansion because you see that expansion usually takes time. So these type of questions you need to know very well. So if for some reason you are interested in finding the coefficient of this term. Okay, but let me ask you one question. Do you expect that this will be one of these terms? And why? For example, if I have given you x to the power of 6, y to the power of 13, and ask you the same question, what will be the coefficient? So the question, let me repeat the question. Instead of 5, I give you 6. X to power 6, y to power 13, and ask you the same question for the same expansion. What would be the answer? So it is 0. The coefficient is 0. It's not included because it is important to realize the sum of these two powers should be this total power here. And that is here. Okay, good. But if you want to answer this question, this is my recommendation. That's up to you. I would write the formula for this. Okay, so what I do, I would write 3x minus 2y to the power of 18. And then I write the formula in front of me. So I write k goes to 0, but instead of n, I put 18. And then here I write 18, choose k. But the x here is this one. So this becomes 3x to the power of n, which is 18, minus k. And then the second term, which is minus 2y to the power of k. Okay, let me ask you one question. How many terms are in this sigma if I open it up? I have to put 0, one term, I put 1, another term, up to 18. How many terms will be at the end? Yes? 19. So remember, the total number of terms in the sigma expanded is 1 unit more. Because you not start from 1, you start from 0. So remember that. Okay, then the next step that I will do some simple calculations inside the sigma. So sigma goes from 0 to 18. So you see that I will have 3 to this power and minus 2 to this power. And I also have this. So let me write them in one place. So it becomes 18, choose k. And then I will have 3 to the power of 18 minus k. And then I will have minus 2 to power k. And then I will have x to this power, y to that power. So this becomes the total expression you see here is called the coefficient. So don't think that this is only coefficient. Yes, this is only coefficient if the numbers are 1 here. But if you have extra numbers here, you have to consider the whole package as the coefficient. And then you want to only to consider this. So this combination appears when k is 13. Yes? If I put k equals to 0, it gives me x to the power 18, y to power 0. If I put k equals to 1, it gives me x to the power of 17, y to power 1. So I ask myself, which choice of k will give me this combination? Which choice of k will give me that combination? It is extremely simple to see that I have to choose k equals to 13. Yes? So we have to choose k equal to 13. If I choose k equal to 13, which is somewhere between 0 and 18, of course, then this term becomes exactly this combination, and the coefficient is equal to this expression, k equals to 13. So the answer would be 18, choose 13, 3 to the power of 5, multiplied minus 2 to the power of 13. You really don't need to calculate anything. If you want to, of course, you can find a number, but that is not very important here. So the important thing is that being able to write the right combination for the coefficient. Is that clear? Okay, another example I give you, and then there will be one more topic that I will complete this whole thing on Thursday. No, Thursday is
Yes.
taking some time. Yes.
Oh, yeah, that's right.
Okay, so I need one more session to complete it, but of course everything more or less is finished. Okay, another type of, let me give you another exercise here. This is also a good question. Okay, so here we write this. What is the term independent of A in the expansion of this expression? So if I can see it, the fourth A to the power of 3, and then plus 1 over the third root A squared to the power of 17. Yes. So here it's an expansion given to you. Yes, it's a binomial. It's related to binomial theorem, but the first term is a little bit more involved, and the second term as well. You want to raise it to power 17. It means that you have to use the binomial theorem to expand that. But because A appears in the denominator in 1 and appears in the numerator in 1, so you might face this situation that the A's in the numerator and the A's in the denominator are totally gone, and then you get a term which is independent of A. Yes? Is that clear? So for example, if I give you x plus 1 over x to the power of 2, it's a Math 2C problem. This becomes the first one squared, 2 times the first one times the second one, and the second one squared, yes? But then look, if I simplify everything, this x and that x are cancelled, so what I get is a term in which x is not involved at all. That's what I mean for this more complicated expression. So I want to see what is the term independent of A, if any, in this term, yes? Because, for example, here, if I choose x to power 2, I will not have such a term independent of x. But if I have done it right, so there should be a term independent of A in this expansion. Okay, let me solve this one as well for you, and then we end this lesson. We continue one more session for this. Okay, so let me solve here. You have the formula here. And then this expression is playing the role of x here, and that expression is playing the role of y, and in this problem n is 17. So what you are supposed to do is this. This is my recommendation, to do it patiently and write everything in front of your eyes so that you really know what to do, yes? To the power of 17, this becomes sigma, k goes from 0 to 17, and then you have 17 choose k. The first term to the power of n minus k, so the first term is the fourth root of a cubed to the power of 17 minus k, and then multiplied by the second term to power k. Second term is this one, so this becomes 1 over the third root of a squared to the power of k. This is the whole mess, actually, if you really want to expand this expression. But you want to find the one which is independent of k, independent of a. Do you have any suggestions? How can I find that particular value for k? Yes, Amor?
Can't you do like 17 minus k?
Yes.
Plus k should be equal to 0. And then when you find k, you can just put it in.
Your strategy is correct, but technically you have made a mistake here. Because you are adding this one and that one. Yes? If I understand.
Because you multiply the 8.
No, but the bases are not still the same. Yes? So you have to make the bases the same and do the same thing. So your strategy is correct, but technically you made something wrong. I cannot add these exponents right now because this base and this base are different. I have to make them the same base and do the same thing as Amanda mentioned. Okay, so what can I do for that? Hopefully you remember the correct formulas, yes? The nth root of a to the power of n can be written in the fraction form, n over m. So exactly, I will do this. So this becomes sigma, k goes from 0 to 17, and then I have 17 choose k, and this one is 3 over 4, so it becomes a to the power of 3 over 4, but I have to multiply it by another exponent there. And I will do the same thing here, but this is in the denominator, so it becomes 2/3, but I bring it up, so it becomes a to the power of minus 2/3 k. Yeah, so what I have written, is that understandable for everyone? Yes? So this becomes 2/3 if I use this rule, but it is in the denominator. I bring it up, it becomes a to the power of negative 2/3, and then I multiply the exponent by k, so this becomes this. Now that's exactly what Amanda mentioned. You see now, I have two powers with the same bases, and then I want to add the exponents. Yeah, so this becomes sigma, k goes from 0 to n to 17, and then I have a to the power of 3/4 17 minus k minus 2/3 of k. Oh, sorry, I forgot to write. I would write 17 choose k here as well. Okay, now what is happening? I have to make the exponent equal to 0, yes? Because I want to have a term independent of a. The only way that I can get rid of a to make the term independent of a is to make this equal to 0, to see if it's possible or not. So this motivates me to put this equal to 0. And then I solve this equation. So for example, I multiply everything by 12 to get rid of the fractions. So it becomes 3 times, it becomes 9 times 17 minus k. This becomes 4 times 8k, I move minus 8k is equal to 0. So 9 times 17 is how much? 1956, 146 minus 17k is equal to 0. Is that right? Yes, and then this means that k is 146 divided by 17. Did I? No, I think I made it wrong. Yes, 90. This is 156. If that is the case, this is not working. Yes, is it divisible by 17 or not? Yes.
It's 153.
Ah, yes, 9 times 17. Yes, thank you. 3. So this becomes what? 3 divided by 17. I hope that this, if this is not divisible, by the way, what is the answer?
9.
If here it is 9, so you say, I agree, it's 9. It's divisible, so I get a whole integer. But assume that I get 152 divided by 17. Then what is the answer to this problem? You would say there are no terms independent of a, because that k should be an integer. In this case, it is. So the k is 9. But be careful, what is asked in this question? In this question, they have asked you what is the term independent of a. So when you found k, you have to go and plug it back into the formula. So if I put k equals to 9, if I have done the calculations right, this becomes 0, a to power 0 is 0, this becomes 17, 9. So the answer that you have to provide for this problem is not 9, is 17, choose 9. Yes? Because they have asked you for the term independent of a. Yes? So you found k, but you need to tell me what is the term. They haven't asked you. If they ask you which term, what is the answer? Of course, which term is not a good thing, but if you keep the order, which term? It's 10, not 9, because the term number is 1 unit more than the k value. So if they ask you which term, if you consider the order, then that is the 10th term. If they ask you what is the term, then you have to give this answer, not just 9. Is that clear? Okay, so officially most of the part of this lesson is finished, but I need one more session to give you more examples regarding this and complete what is left a little bit over. And then we are done. Any questions? Okay, thank you.